Okay, so on the multiple choice test on the AP exam, they're really going to hit hard the idea of Le Chatelier's principle, and that's where you stress the system and see what happens. Most of it's really straightforward as far as like adding a reactant, taking a reactant away, even the pressure stuff with the volume, that's not that bad. There's a couple tricky things that you don't already know about adding water if you have like a solution, and then also with the heat, that can be a little bit tricky sometimes. So I'm going to make sure you got all that, and then look at Q and K. So, moving on, maybe, there we go. Is that the first slide? Okay, so how can you tell if a system is at equilibrium? So, the equilibrium concept from yesterday, that capital K thing that we did, it tells you after those reverse and forward rates are the same, what we're looking at as far as is it geared toward the products or is it more toward the reactants? And if it's a little number, remember the equilibrium lies to the left. Remember if it's less than 1 or less than 0.1 really, then it's going to lie to the left of the reactant side. If it's a big number, then that means the top of my equilibrium expression is big, and so it's going to lie to the right. Are you okay? Okay. So what we're going to do, what chemists can do, is they can actually look at the concentration of the different reactants and products and do this same math. And if they get the answer the same as the equilibrium quotient, or constant, excuse me, then it's at equilibrium. And if this value, this Q value, is different, then it's not at equilibrium. So let's look at an example. So my equilibrium constant for this reaction at 227 degrees Celsius is 0.042. So I know that I'm mostly reactants at equilibrium. Okay? All right. So the chemist tests and finds that the concentration of the different reactants and products are all these things. How can we tell if it's equilibrium? Well, you're going to take these concentrations and you're going to plug it into this. If you get 0.042, then you're at equilibrium. And if you don't, then you're not. That's all there is to this. Okay? So let's look at their way of doing this. Notice from the reaction, which you have on your paper, my products are SO2Cl2. So this guy goes on top because it's a gas, so I can write it in there. And the concentrations of these guys will go on the bottom. There's no coefficients, so they don't have any powers. So there's my product, there's my two reactants. These are the concentrations that they gave me on the last slide. You fill that in and push the buttons on your calculator, and you find that Q is equal to 15.6. A minute ago, I found KEQ, or KC, same thing, was 0.042. So is this at equilibrium? No. And I really like on the Bozeman video, and I'm going to use it, I'm stealing his idea. If you take a number line, K was 0.042, and Q is 15.6. To get to equilibrium, you want to get to K. To get to equilibrium, it's going to have to shift left. If you're taking the AP exam and this is a 2-point question, it's totally worth 7 seconds of your life to draw a number line and make sure you're not screwing that up. Okay? I like that. I think that's great. Do you get me on the number line? You're looking for it. You good? You liked it? Okay, good. All right, great. So the system has to meet products. So gonna have to go left, and that's how you know for sure. So there's another. I mean, they did that. Yay. Let's see. So that's gonna. These guys are gonna continue to increase until Q equals K, and that's what I just explained. The number line will knock this whole slide out for you. Okay. Like that number line explains all these words. If Q is greater than K, then the reaction is going to proceed to the left. That's what just happened on the example. If Q is less than K, then the reaction is going to proceed to the right. And then when Q equals K, then it's at equilibrium. So you can memorize all this, or you can just draw a number line. I'm going to go with drawing a number line. I would rather see it and understand it than memorize stuff, because turns out there's a lot to memorize in here. That's what I think. Okay, so Listen to the sound of my voice. You hear it? Do you hear my voice? Okay. This number, this equilibrium, okay, this little guy. The only way you can change K for equilibrium is by changing the temperature. Okay? That is the only way you can change it. So it doesn't matter if I add products, it doesn't matter if I add reactants, it doesn't matter if I squish it or add, even if I add a catalyst, that doesn't change. If I look at kinetics, not the same stuff, hanging on the wall from last week, not the same stuff. This K, this rate constant, for rate loss, this K changes with a catalyst. The catalyst is going to speed it up. The higher this K for rate loss, the faster the rate, remember, because this number is bigger, so this number is bigger. This number is constant at a constant temperature too. So they both stare at that. You change the temperature, you change the K's. This ain't the same K. This K goes up when you add a catalyst. That K don't care. Okay? This K for equilibrium, the equilibrium constant, only changes the change temperature. That is the only way, and then we use that to trick you. Are you good?
That doesn't matter.
What?
Because that one doesn't matter about time. Like.
Right. And so, yeah, if I add a catalyst, it will get to equilibrium faster, but at equilibrium, my ratio of products to reactants is the same. So good, yes. All right, so if I add pressure on a system at equilibrium, Q is going to change. And once it's reestablished, though, Q will equal K EQ once again. This changes equilibrium concentrations, but it does not change the value of KQ. Okay? Only temperature does that. I'm going to say that a lot, and I don't care. So this is a really, really typical kind of question. All right? If I look at this, it doesn't matter what mole, it doesn't matter what kind of gas I'm talking about. It could be a huge gas particle, little gas particle. It could be something like oxygen gas, or it could be a huge hydrocarbon. Doesn't matter. We're doing ideal gas law here, and I know like the larger ones kind of slow down, they go a little slower, blah, blah. Doesn't matter. Doesn't matter. I have, where's my magic marker? It is magical. I have 1 mole, 1, 2, 3. So I have 4 moles of gas on the reactant side, and I have 2 moles of gas on the product side. It does not matter what gas I'm talking about. If I squish the gas down, I increase the pressure. So this increase in pressure is going to shift the equilibrium towards the side that has the least amount of moles of gas. If, and they'll use this to trick you too, if this 3 wasn't here, no 3, I have 1, 2 moles of gas and 2 moles of gas, you squish it, equilibrium don't change. Okay, so that's something I've seen a lot. How do you feel about that? So if you look here, there's my N2 and my H2. Maybe, whatever, they didn't say. I should have 3 times as many hydrogens, but I'm not. Oh yeah, that works because you have the N is the nitrogen, because the 3 red ones is the hydrogen. Anyway, it doesn't matter. It's not to scale here. Anyway, when I squish it though, add pressure, and I increase the pressure of the system. Is that better than squishing it? I'm sorry. Equilibrium is going to shift to the right, or to the product side, because it has the least moles of gas. That's the first one. Any questions? Does that soak in? Okay. When you decrease pressure, when you expand the container, it is going to try to fill that container back up. So it's going to shift toward the side that has the most gas particles, or moles of gas. This does not change the equilibrium constant, because you didn't change the temperature. So equilibrium is going to shift to the left, because I have 4 moles of gas up here versus 2. So same stuff, just backwards. How does it make you feel? You look kind of bored? Good. When people look bored, take that as a good sign. I mean, for a minute. So increasing concentration. This one is, I don't think anybody missed anything on the quiz with this yesterday. Very straightforward stuff. Does not change the equilibrium constant. So if I add more NH3 to the system, if I add more of this guy, then it's going to shift away from it, right? So, whoop. Oh, sorry. So I'm adding it. It's no longer at equilibrium. So what's going to end up happening is it's going to shift toward the reactant side. I do want to take a second because I did take your test and make the study guide last night. I want to show you something. So let me see. Flashbacks to yesterday. There's my axis. Let's say when I'm at equilibrium, right? That last one did say you start at equilibrium, then you add NH3. If it didn't say that, let's pretend. So here's your NH3 concentration. Once I add the NH3, immediately you're going to see a spike, and then it'll go back down once equilibrium is reached. This new value here is higher than the original one, but this is a very quick process. At the end, though, it's going to be higher than it was at the beginning. You know, like memorize that picture, maybe draw it to the side. When you put a stress on the system, there's an immediate shift to get it out of the system, to get this stress to shift to the other side. But
what's the difference in like change in stress?
same thing. Oh, same thing. Yeah. That was kind of missing, so I wanted to add that in. So equilibrium is going to shift to the reactant side to reduce the stress or reduce that change. But stress is usually the word that's used. All right, so if you decrease concentration, then the equilibrium is going to have to shift in the direction that's going to increase the concentration of that species. So again, that doesn't change KEQ. So if we actually come in here and at equilibrium, we have 11 NH3s, 4 N2s, and 12 H2s. What's going to end up happening if I remove some of my ammonia, then I'm going to shift the equilibrium back toward the product side to make more. This is really, I find this to be very simple. The College Board really likes it to our questions, which is good for us. There's a bunch of test questions like this on your test, like 7, which is a lot out of 30. But that's just very indicative of what's actually on the real exam, because that's where I'm pulling them from. How do y'all feel so far? Still good? Happy times? All right. So this is one that you might not have saw or seen or something in your homework. If you have, I'm just going to go ahead, doesn't change anything, right? If I actually add more water, like if I have a salt, some kind of ionic compound in water, and I add more water, it's going to shift to the side to make more ions. Now let me tell you something about HF. We haven't done acids yet. That's next week. Good times. HF is actually a weak acid. All the other hydrogen and add in a halogen like chlorine and bromine or whatever, you know, you're going to have strong acids. This one's a weak acid. We'll get into why that is next week. But in solution, you can see that most of the HFs do not dissociate. Do you see my little picture here? So most of them are still stuck together. If you add more water, though, you basically, now listen to me, if I think about this like molarity, right? If I add more water, and this, I mean, there's bajillions of HF particles in there, but if this is a 14 molar solution and I dilute it down, so it's 8 molar, I've decreased the concentration. Okay, so what I'm going to do, or what's going to happen with an equilibrium, it's going to shift toward my ions to the dissociated side to add more to it. So that's probably the only one that you didn't see in your homework. So if you add more water, it shifts to the dissociated side. And basically it makes your solution more concentrated by dissolving more. Y'all good still? Yay! So temperature, I actually have this, I'm going to show you. I'm just going to skip a little bit. I actually have this stuff in a tube. I have this stuff in a tube. Now this is not the question, but I'm going to show you this reaction. Guys that were in AP Environmental Science, the nitrogen in the atmosphere and the oxygen in the atmosphere, when combined with heat, like in combustion during a motor or any kind of power plant, they will fuse into NO gas. And this is where I get photochemical smog. And this is also where I get nitric acid or acid rain. Does that sound like something? The heat from combustion just takes the nitrogen in the air and oxygen in the air and they fuse it together. I mean, I know I said that a lot. But heat's on this side, right? When you have, so this is endothermic or exothermic? Endothermic. Okay, so my enthalpy value for this reaction, if it's endothermic, it's going to have to be a positive number because energy went in. So it's going to be greater than 0. Did I lose y'all there? Because I'm telling you, the heat from combustion makes these happen. Now look, I mean, we haven't even got to this slide yet. At room temperature and normal atmospheric pressure, your Kp is 1 times 10 to the negative 30. That means that at room temperature, we're going to have mostly nitrogen and oxygen in the atmosphere and not a bunch of nitrogen monoxide. Is that what you're experiencing right now at room temperature and normal pressure? Yeah. There's not. You don't want a bunch of nitrogen monoxide in the room. That is caustic and it causes acid rain and it is a greenhouse gas and it's chemical, photochemical smog component. That's not in this room right now because we're at normal temperature and pressure. Now, if I go in and I actually, what I have in my little tube, I haven't tried the tube out yet, by the way. I have no idea if it works. So I found it. So, Miss World told me about it. She was like, somewhere in a tube somewhere we had this stuff. And I remembered putting it in a cabinet, but I kind of forgot about it. So on this reaction, we can tell it's exothermic. So if we cool it, if you cool down an exothermic reaction, it's going to shift toward the side to add more heat. So like I said, if you add in and you write in the words heat to the correct side, it makes it very easy. Don't skip that step. You're not helping yourself. If you add heat, you're going to shift the equilibrium away from the side with heat. You just, like I said, if you'll take that, if I heat this up, this is an exothermic reaction. If I heat, basically if it's in a chamber or beaker or whatever, and I add heat, it's going to shift it toward the reactant side. And this is just what I did back there, except the reaction I did back there was an endothermic reaction, so it had heat on this side. Yes, sir?
So you do that as like a reaction?
Yeah, you absolutely need to take the second and write it in. Yes, sir.
Are they going to tell you that it's exothermic?
No, what they'll do is for example, for this one, this is the Haber process. This is one of their favorite ones. They're always going to use this, okay? And so on this one, it'll have delta H, and I don't know the actual value, but it might be like negative 212 kilojoules per mole or whatever. And then you'll know, because that's a negative number, that heat is leaving. That's how to tell. How do you feel about that? And if the delta H is a positive number, then you know heat came into it, it gained heat, and then you'll know to add heat to the reactant side. You're about to get a lot of practice with all these.
Yay!
Yay! All right, so Q and Le Chatelier. Basically, worst case scenario on the AP exam, they may give you an initial equilibrium constant. So in this case, Kp is equal to this, and then they'll tell you, look, a new temperature. If you have a new temperature, they're always going to tell you a temperature with your Kp because it's dependent on the temperature. But they'll give you a new temperature, and then they'll give you a new Kp, or they'll ask you to find which way it's going to shift, or they may ask you to find the concentrations or the pressures. I spent some time last night because you guys had asked me, and I look back at my notes. I have a folder like this thick of equilibrium problems I did this summer. That's all you do in Gen Chem 2 is like ice tables and stuff. And I feel really comfortable with this stuff. But y'all were asking me about the Kp expressions. Like if you look on your formula sheet, a couple people asked me, and I was just like, And I look back at all my notes from this summer, and I looked at release exams and stuff with the Kp, and it popped up like twice out of, I don't know how many other problems that I did, with the concentration being in brackets versus parentheses. If they do give you partial pressure, like this guy, and I'll write the equilibrium expression for this one in just a second. You do need to use parentheses, and I told you that yesterday. But do you see how they have like a capital P and then like a little c, a capital P, and little d? That's when we're going to use the subscript as the name of the gas. And so when you go to write it in before you fill it in, you do need to do that. Let me show you what I'm talking about so you don't freak out. So for this guy right here, okay, I can remember that. So N2 and O2 gives me 2NO. And then they gave me stuff in atmospheres. When they give you stuff in atmospheres, that's a pressure value. Okay, so you're gonna be like KP, and then you're gonna need to put the pressure of NO, and then square it. Do you remember when we did like we did partial pressures before, and then we did like the mole fractions? The names of the gases were these subscripts. And so when you are given stuff in ATMs, before you go to fill in your equilibrium expression, this is the correct way to put it. I mean, and I've said that, but I think I need to back up and punt on, oops, I just messed that up. Don't do that. Do this. It's kind of a habit. I'm going to say the other way is way more common. I did it again. Don't do that. Sorry. I spent my summer doing this, so I feel like I'm qualified to be like the other way is way more common. It's pretty fresh in my mind. Yeah. But this is the right way. And then you can go in and fill them in. Okay? So, going back to that problem. Let's actually do it now. A chemist mixes 80% nitrogen and 20% oxygen by moles in a vacuum and finds that the total pressure is 1 atm. Do they give you the partial pressures?
No.
Do you know the total pressure? Can you figure out the partial pressures pretty quickly? So if the whole thing is 1 atm, then if we look, I think they have it on the next slide. Pretty simple stuff. The initial partial pressures for nitrogen, I have 1 atm and 80%. So I have you totally need to write this down. You writing? Go team go. Is this already on paper? I don't think it is. So I just took the total pressure and then I multiply it by the percentage there. And then the oxygen is 20%. So this is 20% and multiply by 1 atm, and I get 0.20 atms. So that part's pretty chill, right? Let me go back because I don't remember what they were asking me to do. Find the equilibrium partial pressures at 25 degrees. So this is where that ice table comes in. And I'm just going to go and do my own little thing here. Will y'all help me out with the numbers? I can't. See if I have some of them written on my paper. So I'm going to start from the top, taking it from the top. I need to practice, apparently, writing this correctly. Oh, I did it. Okay. And this guy's squared. And then I have, just practice it, embrace it. So far, so good. And then I have, the reaction is N2 gas plus O2 gas. And when you do an ice table, I mean, it really is a rice table. At the top line, you always write the reaction. Yes, because they'll come in. Just wait. Just wait. Just wait. Not today, not tomorrow, but later. You'll see. All right, so there's my reaction. I have my initial, my change, and my equilibrium. At the beginning of this, how much NO did I have? None. 0, okay? And then I'm going to have my, I'm going to have my initial for the nitrogen is 0.80 atms, and then my oxygen was 0.20. Y'all good so far? This is good stuff. So this is going to go down by x, because my coefficient is 1, down by x, and this is going to go up by 2x. And so here I have 0.80 minus x. Then I'm going to draw the line so it doesn't get all blurry. 0.20 minus x, and this guy's 2x. Now before I even do anything, my Kp value was 10 to the negative 30 or something crazy. Right, so can I negate those minus and plus x's? Yeah. And And there's actually an example later on this PowerPoint where you do the quadratic formula. I'll show you what you have to do if that ever happens. I don't think it will. You just do the quadratic formula like you do the quadratic formula. But the deal is, one of the answers will come up being negative, and you can't have a negative concentration, and that's how you know it's the other one. Anyway, so now I'm going to fill these suckers into that, and my KP value they gave me was something. What was the actual number?
Oh,
Was it 1.0?
yeah.
Times 10 to the negative 30?
Yeah.
Alright, and that's equal to, and I'm just going to fill this guy in. So I have 2x squared. And then on the bottom I have, and I'm not even going to write the x's. I'm not even going to write them. 0.80 times 0.20. Alright, so now I'm just going to start simplifying. 2x times 2x. If you're not that great at algebra, it's a good idea just to write out like 2x and 2x and just make sure you don't mess up. But, whatever. So that's 4x squared, right? And that's just going to be over 0.16. And that's equal to 1.0 times 10 to the negative 30th. To isolate my variable, I'm going to multiply both sides by 0.16. I like that. Doesn't that make you happy sometimes when you're not in chemistry? Makes you happy. And we can actually, apes throwback right here, right? I did this without a calculator in my planning period for fun. But I have 4x squared, and then that's like 1.6 times 10 to the negative first. So you get I guess, 1.6 times 10 to the negative 31st. Or do you add them? Is that right?
That's right.
See? That's good stuff. That helps you a lot in life. I sound like such a nerd. But then you divide both sides by 4. And so, this exponent is 10 to the 0. And so it's going to be 0.4 times 10 to the negative 31st. Yeah, is equal to x squared. And square root, we have to do x equals 2 times 10 to the negative 16. Yeah. And it's 2.0. I tried not to run out of room today. I did a little bit better. I'm trying. 2.0 times 10 to the... And the worst thing about these questions is when you find x, you ain't... in math class when you find x, you're like, yeah, I'm done. And then on this, you're just not done. Sorry.
No.
Okay, so my equilibriums here, remember we ignored that x here. So my equilibrium values for N2, still very much the same. And then right here, my equilibrium value for NO is 2 times this. So 2 times 10 to the negative 16 is just 4.0 times 10 to the negative 16. How does that make you feel? Okay? Okay, cool. And that makes up for that one. Oh, let me show you something. That's a bad one to show you. I want to show you the thing that's on the test. What I'm gonna have to do is I'm gonna end up forgetting, and then when you're taking that test, you're gonna hate my guts. That's what's gonna happen. Because you're like, how do I do this? Anyway, if the temperature increases in your KP here is still kind of small, but notice it's not less than something times 10 to the negative 4th, is it? So this only happens, I've only seen this one time or 2 times, is when you're dealing diprotic acids in the second, never mind. When that second hydrogen gets given away, blah, 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 you'll see later. That's the only time I've really actually seen this. So that's what we just did. Did all this. And like I said, you can ignore that, and they get all the same answers as us. This is when KP is 0.0025. So same ice table, same everything, same setup. So you would have to make a new ice table. But at the end, when you set it equal, it's now equal to 0.0025. Now, when you end up simplifying, see how this bottom answer right here has your x squared and your x and your 0.16 is negative x. But Y'all sang the song in math class for the quadratic formula, right? Did y'all all do that? Who's shaking their head no?
We have this together.
Negative
We
b.
have had this together in class.
Okay, who's never heard negative b plus or minus square root? Whoa, Hoss! Wait a minute! Wait, no. I'm singing a song. Who's heard that song before? It don't even matter if y'all failed the AP chemistry exam. Just time out. I'm ready. No, I'm gonna write down the quadratic formula. I'm gonna sing you a song. Negative b plus or minus square root. B squared minus 4ac. B squared minus 4ac. All over 2a. What's wrong with y'all?
I'm trying to get the schedule is fun.
Negative b plus or minus square root.
Yeah.
Oh wait. Do they solve it? Do they? I don't know. They don't have music. Negative b plus or minus square root. B squared minus 4ac. All over 2a. Such a good singer. Anyway, that bottom part of that fraction that didn't work out for us, you stick all that in there, and one of them is going to be a negative number, and it doesn't work when you put it back into the ice table. So, positive number. We don't have to do that. I checked a lot. Oh, did you trust me? Okay. Anyway, so that's the numbers they get at equilibrium for this new value, and that's good. I think what I'm going to do, this guy is a whole nother fun party, and it's not hard, but like, I'm good to stop with this, and this is one little thing, and it's real quick, but I'm just going to hold off on this until tomorrow, and I'll just be like a 10-minute little PowerPoint, and then we can do some review and stuff and free lab things. Let me tell you what I need. All right, so I looked through all these. Most of them are not math. Most of them are which way does the equilibrium shift if you do this. Look at me in the face. That's what most of the questions on the AP exam are. So you have to say left or right. I think you can handle that, can't you?
Yeah.
I don't feel bad for you. I don't feel bad. You're fine. Most of it's not math. For right now, because I haven't taught, go ahead and skip 20. If you want to do it for like extra credit, you can. And then on 21 through 24, those are the ones we're going to have to look at tomorrow. So 21 through 24, don't skip it forever, don't mark it out. But we'll come back to that tomorrow. It's really straightforward. Do y'all kind of remember how with Hess's law we would add up reactions and